Good morning. Today we are discussing laws of physics in anesthesia. These are the quite common question being asked in vivas and even in the MCQ exam of anesthesia. First I will discuss gas laws. And in gas law you can remember three gas laws. First is Boyle's law, second is Charles' law, and third one is Gay-Lussac's law. And it can be denoted as first law, second law, and third law of the gas, and it is applicable in ideal gases. Coming to the Boyle's law, it says if the temperature remain constant, volume of the gas will be inversely proportional to the pressure of the gas. It can also be written as Vp is equal to constant. Okay, so this is Boyle's law. Coming to the Charles' law. So what does Charles' law says? That if pressure is constant for an ideal gas, volume of the gas will be directly proportional to the absolute temperature of the gas at that time. It can also be written as V upon T is equal to constant. So third law here is Gay-Lussac's law, and definitely it relates the remaining two components, that is pressure and temperature. So it says if the volume is constant, then pressure of the gas at that time will be proportional or directly proportional to the temperature at that time, and it can also be written as pressure upon temperature is constant. So just to as a revision, Boyle's law, it says if temperature is constant, volume of the gas is inversely proportional to the pressure. Vp is equal to constant, while Charles' law says if the pressure is constant, volume is directly proportional to the temperature, or can be written as Vt is equal to K, V upon T is equal to K, while Gay-Lussac's law says if the volume is constant, pressure is directly proportional to T, temperature, and P upon T is equal to K. This is about first, second, and third gas law. Then we will go to other physics laws being utilized in anesthesia, and one of the principles which being used is called Bernoulli's principle, and it is actually responsible, or you can say describes the flow of a ideal fluid or gas inside the tube, and this principle can also be denoted by Venturi effect, which is being used in our Venturi device, being used in anesthesia very commonly, anesthesia and even intensive care. It says the pressure decreases at a place where velocity of fluid increases, velocity of flow of fluid increases. So if some place will increase the velocity of flow, that will lead to decrease in the pressure. It can be denoted by this diagram. So if the fluid is forced to flow through a narrower tube, it will lead to increase in the velocity of the fluid at that place, and that will ultimately lead to decrease in the pressure at the site. So you can see the velocity is increasing in the narrower part of the tube, while it goes back to the lower velocity when it comes out of the to the wider tube, but it leads to decrease in the pressure at the narrower side of the tube. We can discuss it in case of Venturi device, how it works. So if you make a narrower tube and it causes high speed of gas flowing, usually oxygen flowing through the narrower tube with high velocity and being delivered to patient by a mask usually. As the velocity increases at the tip of narrower tube, the pressure around the tube decreases, which lead to a kind of suction pressure, and it sucks out air around the tube, leading to increase in the volume of the gas delivered to the patient, and it delivers at a constant concentration. That's why it's also called as constant flow device and also Venturi device. So another effect which need to be discussed here is about the fluid is called Quanda effect. It happens when a liquid flows around a convex surface or fluid even. So what it does, that if the fluid is flowing in this straight line, it leaves its own track and actually follows the surface of the convexity, and the flow goes to the other direction, which is almost tangential to the to the surface at every point, leading to diversion of the fluid. It's called as Coanda effect. Another topic law is to be discussed here is Henry's law, which says that amount of a gas in the liquid dissolved in the liquid is directly proportional to the partial pressure of the gas, which is in equilibrium with the liquid at the time. So the amount of gas dissolved in the liquid will be directly proportional to the partial pressure of gas in equilibrium with the liquid. That is important because every time you have that says that all the gases is directly proportional to the amount of means directly proportional to the partial pressure. So it is a kind of indirect denotation of partial pressure. So just to remind, velocity of the flow actually if increases lead to decrease in pressure. It's called Bernoulli's principle, being used in venturi device to give a constant flow of gas to the patient, not depending on the respiratory rate or tidal volume of the patient. While so the main thing is that it lead to fixed gas delivery, while the Coanda effect is leading to the fluid following the convexity of the surface rather than flowing in the straight direction. And Henry's law says amount of a gas dissolved in a liquid is directly proportional to the partial pressure of the gas. Another topic is Avogadro hypothesis, uh, which says if the volume, temperature, and the pressure of a gas is constant, then whatever is the gas will have an equal number of molecule in equal volume. So there will be equal number of molecule in given volume. So it doesn't matter whether it's oxygen, nitrogen, carbon dioxide. If the temperature and pressure is same, the same volume, the number of molecule will be similar. And actually this gives a concept of mole when we say 1 mole of the gas is equivalent to Avogadro number. Another principle which is or which is related with the flow of the fluid, is Higgins-Poiseuille's equation, which actually decide the flow rate of the fluid inside a tube, which is equal to pi, then pressure difference at the end of the tube, then radius to the power 4 divided by 8, then viscosity, and then the length of the tube. So just to remember, the most important thing is that flow is directly proportional to the r to the power 4. That is very important. And when we say like that, it's the most important thing to decide the flow rate, as it increases by radius to the power 4, while it also says that it is indirectly proportional to the length of the tube and also the viscosity of the fluid. So as the length of the tube will increase, flow rate will decrease, and as the viscosity will increase, the fluid will be flowing slower. So this question can be asked by asking like which one is better, whether which tube you will prefer or which cannula you will prefer to deliver the fluid, and you will say the cannula should be wider and should be smaller in the length. So the radius should be high but length should be low. So if the diameter is constant, you will find that flow in the peripheral vascular cannula is higher than central venous catheter, because CVC is usually longer than the cannula instead if the diameter is constant. One of the more another important topic which can sometimes asked in the exam is what is Reynolds number, and to remember it is also another one formula which is related with the flow of the fluid, and it decide whether the fluid will be flowing streamlined or will be flowing in turbulent fashion. And when we say Reynolds number, it is equal to the density, which is denoted by P, and the velocity of the fluid multiplied by diameter of the fluid and divided by viscosity of the fluid. So as the density of fluid will increase, or velocity of the fluid will increase, or diameter of the fluid will increase, Reynolds number will increase, while as viscosity will increase, Reynolds number will be lesser. And if Reynolds number is less than 2000, the flow will be laminar or linear, while if Reynolds number is more than 2000, the flow will be turbulent. So to just revise, Poiseuille's law says flow is directly proportional to the r to the power 4 or radius to the power 4, inversely proportional to the length and the viscosity of the fluid, while Reynolds number says decide laminar or turbulent flow, and it increases with the density, velocity, and the diameter of the tube, while decreases with increase in the viscosity of fluid. Reynolds number less than 2000 means the fluid will be laminar in flow, while Reynolds number more than 2000 says it would be a turbulent flow. I think these are the enough numbers of laws which we have discussed. Um, Nobody will ask anything more than that in terms of laws of physics in anesthesia exams. I will just request you people to just like, subscribe my videos, and feel free to ask any question uh, in the comment. Thank you very much. Thank you very much.